So welcome back. You've heard me talk before, but this time I'm going to talk to you about computational stuff. So my name is Vincent Meunier. I'm here working at RPI. I'm the department head of the physics department. I work with Professor Geet. Actually, I have a couple of students here, maybe taking a nap, I don't know. And so what I'm going to do today and tomorrow is to give you an introduction to density functional theory. Including background noise. So actually what happened is that a few years ago, I created a course, Density Functional Theory, that I taught for graduate students, and it was a 2-credit course, so we met for 2 hours per week, so this was a 30-hour course. There's a reason why it's called a very short introduction, because I used my 500 slides from that course and put them all together here today. So there's a reason why I need a pointer, because I really need to change slides very quickly. That was a joke, by the way. I'm going to try to tell you when to laugh, otherwise it's not going to be funny. And so it's a very short tutorial compared to the full version, that's the point. So I know you guys here, you've had a lot of talks, and you'll have more talks, and some of you are more interested in high energy physics, others more in classical fields, other very different fields. So I am not expecting everybody to ever use density functional theory necessarily, but I think it's easy enough and important enough in the field of material physics that I should really try to spend time to introduce this. And I hopefully probably by the end of today, at the end of this lecture in 1 hour or so, you'll have an idea of how these things work, and also maybe give you an idea about the power of this approach. Tomorrow, depending on where I end today, I will finish my 500 slides tomorrow, or I will actually show you something else. I have not decided yet. I think we will decide that later. Okay, so let me try to summarize again. My goal today is to tell you so that by the end of this hour, you'll know what density functional theory is and how it can be used in materials. Okay, that's my goal. You've heard people talk about DFT. Dr. Sumter probably spoke about DFT. Eduardo Cruz spoke about DFT. Maybe somebody else too. Today I'm going to use a different approach. I'm going to introduce you the theory behind it. Okay, so how we get there. My main problem with DFT, and in fact it's a problem with many computational physics packages, is that people just use them. They usually have no idea what it's behind, but they use them like they would use PlayStation or whatever, right? And you know what? It makes beautiful graphics. It makes beautiful figures. It makes beautiful graphs. You put them in a paper, you write a paper, you have absolutely no idea what the boxes did for you. But you know what? It's a paper. Who cares, right? Well, not really. The problem is you really need to understand what's behind a code before you actually can use it. Well, you can always use it, it's fine, but the interpretation can be laughable, or sometimes you cry because it's really terrible, if you don't pay attention to what's in there. So if you only get this from this lecture, I'll be happy, all right? Okay, so density functional theory. There are different types of density functional theory. One exists in nuclear physics as well. There is also a DFT that people use in experiments that has nothing to do with this, so I'm not going to talk about it. And of course, DFT, you probably have heard that in undergrad as a discrete Fourier transform. That's not any of those, okay? So we are going to do density functional theory today. Okay, so why is DFT important? Well, DFT is important because when it was invented, people didn't realize when it was invented how important it would become. But when it was invented and then computation became more prevalent and more computers were there and more softwares were available, people started to use it a lot. In fact, this is the curve here that shows a number of papers since the mid-2000s, so 2015 is a bit updated, but not that much, in kilopaper, in thousands of papers that were published just with DFT as the main topic, okay? And so it's something that's increasing exponentially. In fact, it's really about here now, and so it's important to know what it's all about really when you want to do this. Okay, so I'm very sorry, but I walk a lot, so you may have to do a lot of workout today if you want to follow me. Or if you have a tether, I can just attach it and then I move on. Okay, so personally, I learned about DFT when I was a master's student in 1997-ish. Those places. I'm not responsible for all the papers there, but I was around here. I was the only student in that class, so that was kind of a very good attention. So the reason being that nobody cared so much about it yet, and then. Chemists hated it, and I will explain to you why chemists didn't like density functional theory. And then they realized they should not hate it; they should use it. So I'm also going to explain to you why why it became so important in chemistry as well. So you see, chemistry started a bit slower. In fact, it looks like it's kind of converging differently, but in material science people do this. So engineers do that a lot. One of the problems is that DFT becomes more and more now a package. There are packages, and people use the package as a black box. As I said before, it's not a good idea. So that won't be you, because you are going to have this lecture, right? Okay. So there was a Nobel Prize that was actually awarded. I can't remember. Was it 1998? Yeah. In chemistry. That was a Nobel Prize in chemistry. That was awarded around these years right here. Okay? Now, what about the different colors? The different colors, chemistry, materials, these are different implementation of DFT, and again, I will explain to you what it's about. What you need to know in DFT is that there is a major approximation we are making. The approximation is controlled, and this is the usual thing that you see for that. Okay, so quantum mechanical problem. So what in quantum mechanics for materials, what we want to know, where are the electrons located? Well, if you're a quantum mechanics person, you say, well, this question makes no sense, because we can't know where electrons are located, right? So at least you can know what probability you can find an electron at a given place. That's what I mean by that. So do not use Heisenberg principle against me. I'm just using the classical description of where electrons are located. So that's what we are trying to do. So we have a quantum mechanical problem, and of course the quantum mechanical problem is to solve this. This equation looks very simple. The big problem is that on the left-hand side we have an operator, the operator H, Schrödinger operator, which is where all the details are located, and this is difficult because what we need to know is a wave function. This is the solution of this eigenvalue problem, and the eigenvalue is the energy of the system. So this is also called a time-independent Schrödinger equation because, well, you know what, the time has been factored out simply because we know that the energy state of the Hamiltonian are the stationary state. So if you know how those evolve with time, you will know how the entire solution evolve with time as well. Okay? I guess this is not something new for you. This is a picture of Schrödinger right here. Okay. So I'm wondering if I have the right presentation because I changed Schrödinger this morning. So let me see if I have. No, this is not the right one. This one is the right one. So I'm going to start from the beginning. No. Okay, so this is Schrödinger. Okay, this is the good one right here. Okay, so Schrödinger equation. So we have to solve this. You've seen this before. Now the wave function here is basically when I introduce wave function in the quantum mechanics course that I teach, I always say, well, I don't like to talk about wave functions. First of all, I like to talk about state, quantum state. So a quantum state is an object, some sort of abstract object that includes all the information you can get on the system. you know that that object has been built, has been invented to include any information you need on the system. That's it. There is no other definition. Of course, the problem is you don't know how to get it, okay? You just know the equation to solve Schrödinger equation, but you don't know how to get it. Now, there are ways to represent those states, and one of them is the wave function. So wave function is really a real space representation of a quantum state. So this is where you see these positions here, which are really parameters. x1, x2 is positions of the electrons, r1, r2, positions of the ions. So this is really what we are looking at. In solid state physics, is what we really try to solve. Now, all the information is in this state, and this course is an extremely complex mathematical object, even this one, which is a function. Okay? Why is it important to know it? It's important to know it because the square modulus of this object, which is, by the way, a complex function, gives you the probability of finding a particle at a given place. Actually, it's really the probability density, but we'll get that in a second. Why is it complicated? Well, suppose you have 3 electrons, okay? And suppose that you use a grid to represent the position of the electron. And the grid has, let's say, 1,000 possible interval on the grid. How many numbers do you need to represent a wave function for 3 electrons in that case? How many possibilities are there? Yes, we have 3 electrons, and we represent the position on a grid which has 1,000 points on the grid for each electron. So how many different numbers do I need to calculate? Well, suppose we can have boson. So if we can have boson, they could be all at the same place, right? So the solution you gave was for fermion, right? So it's 1,000 to the power 3. Do you think 1,000 points is enough to represent, for example, let's take this box, let's take this room here. You see 1,000 points, you think it's accurate enough to find the position? Not quite. Let's say 1,000,000. And let's say I have an Avogadro number of electrons. By the way, Avogadro number of electrons is not that much. I know it's 6 × 10 to the power 23, but it's not that much. You'd have way more than 1 mole of electron in your body. Yes, you didn't know that, right? But it's true. You have many more than 1 mole of electron in your body. Oh, you know how many electrons you have in your body? Anybody wants to guess? Oh, that's a good exercise. Suppose somebody like me, let's say 100 pounds. I'm just, rounding it off. No pun intended. 100 pounds. How many grams? Let's say 50 kilograms, right? That sounds even less likely. But 50 kilograms. Let's suppose I'm all made of carbon, right? So what's the mass of a mole of carbon? It is, I got many different numbers. I got a 12, I got 12. Who else? 12? So somebody with the calculator there. So 50 kilograms divided by 12 grams. How many moles is that? You should be able to do it by yourself, right? It's 3,000. 3,000. Right? How many moles? Hmm? 4,160. Yeah, you see, I did by just like this without preparation, right? So let's say 5,000, right? 4,000. Yeah, but it doesn't matter. Nobody's going to check, right? So let's say 4,000 mole. So how many electrons is that? It's 24 × 10 to the power 27, right? Yeah. Suppose you use 10 points to represent the position of each electron in your body, which, by the way, is very coarse. So nobody has a coarse body in this room. How many numbers do you have to calculate? 10 to the power 27. Can you calculate that on your calculator? You know you can't. It's a lot. It's impossible. And this is just one body, and it's a pretty small one with that, right? So that's the complication of the wave function, okay? This is really complicated. And if you try to even understand things even smaller, let's say, oh, you said the body, it's 50 kilograms. Let's say even 5 grams. 5 grams, right? It's 10,000 times smaller. It's still a big number to calculate. It's still impossible to calculate, right? Yeah, so that's the problem we have in physics. In physics, if we want to look at the atomic scale, we are stuck computationally. We are really stuck. We can't do much. So there are different ways to calculate this. In fact, this morning we heard about Monte Carlo. There is what's called quantum Monte Carlo. In fact, you can try to solve this using quantum Monte Carlo methods. So in that case, instead of having to calculate the wave function at every single point, you sample the space. And by doing that, you actually can calculate all the integrals very reliably, just like you calculate pi this morning, and get information from pure quantum. Right now, I think people are working a lot on that. Right now, the limit is about 12 electron system that you can solve that way. So that's nice because this is, you know exactly what's happening, but 12 electrons, that's not many electrons. But this is developing, okay? So let's see what we can do about this. So this is what you have to solve, right? You have an operator on the left-hand side. Then you have the wave function, then you have the energy, this is the Eigen's value problem, and then you have the Eigen's state right there. And the Hamiltonian looks like this, okay? You guys everybody's a physicist in this room? Who is not? You're a chemist? Nobody's perfect. Sorry, I mean, I used to say that joke. I don't agree with that, by the way. There are physicists that are worse than some chemists. Not many. No, I'm just kidding. Somebody, you know a lot of chemists, don't you? Okay, let's be serious now. That's the only person who took the calculator out when I asked, so that's a good point for you. Anyways, at this level, at this point, you know, when you do quantum chemistry or quantum physics, is pretty much the same thing anyway. Okay, so this is the Hamiltonian, what it looks like in our representation. No, not even, yeah, in the representation of the ions that are, I mean, nuclei that are considered as classical particles. And you end up with something like this. You know, if you were not a physicist or a chemist, anything else than physicists and chemists in this room? Some engineers, maybe? No? Some people, oh, he was leaving? No. Oh, you...
He's in the wrong class. He does work.
2 weeks later, right? Oh, these are all physicists. Oh my God! It's not contagious. Don't worry. Okay, so you end up with this equation that looks awful, but it's really not awful. It's terrible. Because this equation is very complicated, not so much because you calculate the Laplacian here to get the kinetic energy of the electrons or the kinetic energy of the ions, not so much because you calculate the interaction between the ions and the electrons, not so much because you calculate the interaction between the ions, but the one that really kills you is this one. This is the interaction between the electrons. The small r ij, so lowercase r, is the distance between the two electrons. And that one is the terms that's really complicated. In fact, just to give you an idea how complicated it is, even in classical physics we can't solve this. You know, the problem of planets around the sun, this is exactly the many-body effect that we have. This is the interaction between the bodies. So we can do it computationally. Yes, we can do that now pretty accurately, for example, for planets. But for electrons, this is really a different ball game, completely, because we have to solve this quantum mechanically. So, you know, even without going into the details, you know that this term here is going to be really a pain, okay? And this is where physicists and chemists used to disagree on how to solve this. They still disagree to some extent. The reason why they disagree is because you need to approximate this, how you treat it. Okay, so of course, if there was one full solution, people would, at some point, would stop disagreeing. They would just accept it. But here we are still dealing with this using approximation, and DFT is one of them. Okay, So as I said, we have, this is a question that you should know, right? As graduate student, even though some of you will never do solid state physics much more in your life, when you see an equation like this, you should be able to say that this is kinetic energy, this is electrostatic energy, right? This is the kind of thing you should know. This is undergraduate stuff. I used to say it's preschool, but they don't teach that preschool anymore. So at least it's undergraduate. Okay, so the first thing we do is to say, well, you know what, the ions really behave like classical particles. Why is that so? Well, they are bigger, and so they get closer to the classical regime, so we're not going to worry about that so much. So we are going to consider that in a Born-Oppenheimer approximation, this is the name of the approximation, we are going to consider that the nuclei are behaving like classical particles. And in fact, in the Schrödinger equation, we are going to put them as parameters. So this is very different. A parameter is very different from a variable, of course, because all the derivative, there is no derivative that includes the parameters, unless you're trying to do an optimization problem, which we are not doing it at this point. So we end up with this Schrödinger, not Schrödinger, Hamiltonian, which is the same as before. We have the kinetic energy and the Coulomb energy, and then we are going to treat this classically, and we are going to suppose that the ions are not moving fast enough. In other words, the mass is so large that this term essentially goes to zero. So that will simplify the problem somewhat, because now the equation is going to be, we're going to reduce the number of terms in the equation. We're going to use this potential here between the electrons and the ions. So you know Za is the atomic number of this ion A, and then of course the other term we have. So the total energy that we have at the end is the energy that comes from the electrons, that we don't know, we are going to calculate this, and the other energy comes from the ions, which is electrostatic energy. So repulsive, because the ions are essentially the nuclei, it's basically the nuclei, is the atom stripped from the electrons, so they're always positive. So we are going to add this term right here, the nuclear energy. Okay, so we end up with this Schrödinger equation. To be honest, it's not much simpler than the one we started with, but it's somewhat simpler. So far, so good. Any question on this?
No strong interactions.
Sorry?
Strong interactions.
No, we are just consider that one classically. It can be a strong interaction, but it's classically treated. It's basically treated exactly the same way as the planets around the sun. This is pure classical. In fact, the potential looks very much the same. It's 1 over r potential. Instead of being gravitation, it's electrostatic, Coulombic.
So what do you use that other potential term between the electrons?
We still have it. That nasty one,
Yeah.
we still have it. We are not forgetting it. If you see me forget it, just remind me, because this is really the bad one. Okay? Let's see in a second. Okay. Now, we end up with this problem. This is written, this exact same equation as I said before, but written slightly differently. We have the kinetic energy here. We have the interaction here between the ions and the electron. We call it V. And then we have this term here, which we call U. This is the term I was telling you about, 1 over Rj. Okay, so why do we write it this way? Well, we write it this way because in this term here, the electrons do not interact with one another. We just have the kinetic energy and the interaction of the electrons with an outside potential. So basically, the electrons are independent. So if our problem, if we said that this is negligible, right? If we say the electrons do not interact with one another, then the problem ends up with this, which is actually exactly solvable. Do you know how to solve this? There is a separation of variables. Anybody has already solved this ever? Yes, you have. It's the hydrogen atom, right? You've done this. Even chemists have done this. Anybody who took a quantum mechanics course has solved the hydrogen atom. Who has never solved the hydrogen? Who has solved the hydrogen atom? So most of you. The others are taking a nap, maybe. Yes, apparently yes. So this is the hydrogen atom, right? This is right there, but with a larger number of ions, and then of course you sum that. But unfortunately, you have this interaction here that comes, and you know, is even the helium atom, as you know. When you have 2 electrons, you can't solve it exactly. Well, there are ways to kind of find ways to do it, but it's really complicated. Here we are talking about an Avogadro number of electrons. Okay? All right, so let's try to move on from here. So this potential, as I said, is due to ions, so I just put this there. Are you anybody interested in those slides? I can make them available if you're interested in this. So I can just, wherever, you have a Dropbox somewhere, or maybe I give them to Paul and you'll upload them, okay. The external potential right here, we have, so it's the charge between, is the interaction between the charge of the nucleus and the charge of the electron, so it's right here. So that one is actually fairly simple, it's classical. Then you have the mean part, as I call it, or the bad part, which is this interaction between the 2 electrons, okay? So, and of course it's given by this. So this part is the one where we have so much trouble. And this is where we have to do approximation. There's many approximations we can make about it. And this is what we are going to do. Okay, now, I set this is the background we have. So far, nothing about DFT. I didn't tell you about density function theory at all so far. I'm going to start in a second, okay? So we end up with this equation, and we want to do something that's called first principles. If you've done Latin in your high school, or if you wanted to do Latin, or you always wanted to do Latin, you can say ab initio. It means exactly the same as first principle. It means from the beginning, right? So ab initio theory means that you have that equation where I have made a slight approximation with the Born-Oppenheimer, but it's not a big approximation. This is basically saying that if I could solve that equation exactly, I would basically play nature. I would actually act like nature, because I would only use constant of nature, right? Like a Planck constant, charge of the electron, mass of the electron, and I would actually get properties from there. This is exactly what nature does. So if you accept, if we accept as scientists that Schrödinger equation is correct, and that we describe the interaction correctly, if you can solve this, you can exactly reproduce nature. This is called first principle. So you start from the principle of nature, and you get the answer from there. Okay? So this is what we are trying to do. We're trying to find such a theory that's going to allow us to solve this. Okay, so the usual quantum mechanical approach would be to say, I have a potential V of R. So V of R is what, remember, this is the potential, this is the interaction between the electrons and the ions, right? You remember this is the term I presented. So basically that term tells you what's the material I'm looking at. Because the materials, the position of the ions, will actually completely describe V of R as a set of parameters, which are the position of the ions. Now we solve Schrödinger equation, we get the wave function, then you calculate observable. So you of course know what this means, right? You just stick any Hermitian operator there, and then this is actually expectation value for that particular wave function. So this in a perfect world is what you would do. But the problem is that it's very hard to solve this right here. So if we could solve for the wave function, we'd be very happy people, but we can't do that. So how do we go from here? Well, you either give up and become an experimentalist. Yeah, I know it's the worst that could happen, but you can give up, become an experimentalist, or go do some more computer science, because you realize that with all the knowledge you have, you can make a lot of money. So why bother doing science, right? You could do that, but you're not going to do that, right? He's like, yes, I'm going to do that. I just need... I don't want to give you ideas. But hey, look. Some people have to, we have to sacrifice our life to this, right? And we have a pretty good life, believe me. Yeah. Nobody seems to believe me. Okay, so now let's go to the essence of DFT. That's my goal here. So I hope by now you know where we are going, right? We have a Schrödinger equation. It looks easy because we wrote it formally, but solving it is essentially impossible. Do I have to I don't have to show that to you that it's impossible to do it, right? Yeah, I think we all agree. So the essence of DFT is this. The essence of DFT is that we do not need to go through the knowledge of the wave function to make predictions. So remember, Schrödinger equation is an eigenvalue problem. Hamiltonian operator, wave function, eigenvalue, wave function, right? So the density, so the probability of finding an electron in a given place, is just the integral of the wave function over the entire space, right? So we know that. So we know how to do it on piece of paper. The essence of DFT is you can actually calculate the density without calculating the wave function. Okay? So there is no longer wave functions. And this is, I'm going to, because I started this, so I'm going to finish this. This is where physicists and chemists initially disagreed. Chemists said, no, you can't do that. You always have to look at wave functions. You cannot do that. You need, for example, to use orbitals. So orbitals would be knowledge you have of single particles, and then you put them together, you create all sorts of different things like Slater determinant. You probably have heard about Slater determinant. You have heard, and you do all sorts of things that you improve and add higher order solution, which is essentially a Taylor expansion of your solution, and you end up with something like Hartree-Fock, if you have heard about Hartree-Fock. DFT says, no, you don't want to do that. You want to stick with the density right away. Okay? So it's not just a hope that people had. There was a theorem that actually established you can do that, and this is what I'm going to talk to you about now. So let's suppose we can do it. So remember that we have our 50 kilogram of scientists alive. Or even if it's not alive, it's still 50 kilograms of scientists, mostly carbon. And we said what? It was 4,000 moles, right? 10 to the power 27 electrons, right? Now suppose I want a grid with 1,000 points. How many value of my function do I need if I use the density of electrons instead of the wave function? Suppose that instead of having to calculate 1,000 to the power whatever for 50 kilograms, I use a density, so the density of electrons in the body. How many points do I need to calculate for my function, which is in this case density, to get the solution on the same grid? It's not a trick question. 1,000, right? It's just 1,000 because my function, instead of being 1,000 times 1,000, okay, I have to go 10 to the power 27 times. It's just 1,000. So the saving, just the storage, don't even think about calculating, just the storage is extremely reduced. There was a question there?
That's if you just have
No.
If you were to add something else.
No. That's a good question. Even, I'm talking about the density for a collection of electrons.
No, I'm saying that you had something other than electrons, like you had some other
particles.
Yeah.
Oh, you can, I'm just using electrons, but so far you could use something else than electrons of particles.
in addition to.
Yeah, then you have then maybe you have another variable.
Yeah.
That would still be 2,000. And if you have another type, maybe 3,000. But that's actually it's actually not 3,000. I'm sorry, it's 1,000 to the power 3. But still, it'd still be way better than 10 to the power 27, right? Okay. So this is one of the big advantage. The other advantage, of course, is density. This is very intuitive. Density is to tell you where the electrons are. A wave function, not quite. A wave function is a very complicated beast. It's a multi-component function. It's very difficult to represent. In fact, it's impossible to represent on a piece of paper, unless you have one electron or two, maybe two electrons, you can start to think about stuff. So that's another thing that's very intuitive, okay? So that's very helpful as well. So I already explained to you, we already did that little exercise, so I don't have to go through that. So this is a picture that probably many of you have seen. You know, anybody can describe this? It's what it ends up being, but anybody? I guess that is what you did, STM?
I'm thinking what it is.
This is.
I've seen it so many times.
Oh, you should know this. This is part of the culture, right? So what is this, Natalia? Natalia is a student in my group. So do you know what this is? We should have rehearsed this. Okay, what is this? This is actually a picture taken by Donna Eigler and Mike Cromie, I think, was involved in this too. It's an STM image done in IBM. By IBM, it was probably in the 90s. It was one of the first of them. It's called a quantum coral. So basically what they did with the STM, they move, I think it's ions, those guys. They move them in a circle, okay, on the surface. And then what happened is that by doing this, they trapped electron inside. So for people who are more mathematically inclined, what is the function we see inside? By the way, it's an experimental data. What's the function we see here? Start with a B. Oh, that's great. So it's a Bessel function, in fact. And in fact, it's a solution of Schrödinger equation right there. And this is what you're really measuring with your STM is the density of electrons. So you're actually measuring the density. So there is a one-to-one correspondence to what you can measure and actually what you can calculate. This idea that STM measure the density is called the Chertoff-Hamann approximation, for those who care to know. Okay. Now, here comes, in 1964, the theorem that really, really establishes why we can use density as the variable in solid-state physics. Okay? And this famous theorem from Hohenberg and Kohn, right here, and it's called the inhomogeneous electron gas. This was a paper in 1964. I had the privilege to meet Walter Kohn. He passed away a couple of years ago. I met him, actually I share a cab with him from back from a conference. It's probably, it's one of the person you go to a conference. It was a conference, we were about 80 people in the room. And he made a point, he was already an older gentleman at that time. He made a point of asking a question to everybody. Students were there, postdoc, and all the people, they were asking a question to every single talk. And people knew that. He was in the front row, he already had his Nobel Prize, because, by the way, he got a Nobel Prize on the side, as a side job. He got it for the EFT, and he was asking a question, and people were actually waiting for his questions. Because just his question, it was so enlightening just to listen to his questions. So you could actually make, like a report, oh, Dr. Kohn asked this question and this question and this. It was amazing. Anyway, that was kind of cool. So sometimes if you have a chance to see people like this, it's how you see the great mind. And Walter Kohn definitely was a great mind. As I said, he passed away a few years back, maybe a couple of years ago. Anyway, so this another anecdote, if you were interested. Dr. Hohenberg actually didn't keep working on that field at all after this. He started to work in the philosophy of quantum mechanics. We invited him, I think it was 8 years ago, he gave a talk here. And I was talking to him, and I think he's in, I don't want to make a mistake, where he is now. I thought he was at maybe NYU, but anyway, I don't remember. And then it was very funny because we went for dinner, and we always say Hohenberg-Kohn theorem is like, the big deal stuff. And he said, Vincent, you should really tell me what DFT is all about now, because it's been 40 years since I looked into this. That was kind of cool. Anyway, let's keep moving. So what does that paper say? That paper says something very simple. In fact, I hesitated to put the proof of the theorem. I don't have it, but if you're interested, I can provide the proof tomorrow. The theorem says this: if you have a non-degenerate ground state, two different Hamiltonian cannot have the same ground state electron density. What does that mean in simple words? It means that if you have one system, which is of course described by one Hamiltonian, you can only have one density. So if you know the density, you know the Hamiltonian, therefore there is a one-to-one correspondence between the two. In other words, if you can know the Hamiltonian, you know the density. If you know the density, you know the Hamiltonian. This is a one-to-one. It's just a change of viewpoint, if you will. Okay? This is very important, of course. That means that maybe the density is really what we should go after. Yeah.
So in metals, we can have ground states.
Yeah. So it turns out that for this, you can actually, this theorem is actually expandable, but this is what the initial theorem. It's true for any system. Yeah. Of course, you have a degenerate ground state for good question. Let's keep working. You see, don't focus too much on the word non-degenerate ground state. Focus more on the fact that the knowledge of Hamiltonian and the knowledge of the density are essentially the same thing formally, and you can prove that. If you want, I can provide the proof tomorrow. I don't have it in my slides here, though. Okay, so that's what it means. If you know, I mean, that we know. That result is trivial, right? If you know the Hamiltonian, you know there is a density corresponding to it, right? Because if you have the Hamiltonian, there is a wave function. If there is a wave function, there is a density. I'm not saying you can calculate it. I'm saying formally there is that. But so that's not what Hohenberg theorem says. Hohenberg theorem says is the opposite. Is this as well? So this is what's important in the theorem. It means there is a one-to-one correspondence. In other words, if you use two different Hamiltonian, you will definitely have two different densities. Okay? Yep.
So is this like an existent protocol?
Exactly. It's an existent thing. It's not. It doesn't give you the recipe how to get it. Yeah, but that's where we start, right? It's like mathematicians spend 3 pages to say all the conditions, and then at the end you get to the result. But in this case, it's important. So that theorems there tells you something very important. It says that you can focus on the density. It would be so much easier if you had the density directly. You do not need wave functions. You can calculate directly the density. That's all you need for experiment. So let's try to go a bit further with this. Okay, so in other words, there is a one-to-one correspondence. That's what this means. Okay, now here's the thing, and this is where we talk about functionals. Anybody here is familiar, hopefully most of you, familiar with what a functional is? What's a functional? Who wants to volunteer? Yeah. Now, do you know how to calculate functional derivatives? Yeah, but it's not trivial. Anybody is familiar with functional derivatives? Anybody wants to? I can actually provide you kind of a half-hour tutorial on that tomorrow if you're interested. It's actually a bit more complicated than it looks. Yeah, I'm sorry. I see on some of your faces. Yeah, I will be back tomorrow. Sorry.
We'll take it.
We'll take it. You'll take it?
Yes.
Oh yeah, I'm going to do it anyways, but but I like the support. So no, I know sometimes you have to give the impression that people have a choice, but actually you definitely have a choice. You don't have to come. Exactly. You definitely have a choice. So that's the reason why you see we are making good progress now, right? We've talking about density. I've almost spoken about the functional. We just have to talk about theory, and then we're done. So here we have the energy. So remember, what happens is that the energy now depends, the total energy of the system depends on the density. right? The density is a function. We already discussed. Therefore, the energy is a functional of the density. Okay? All right? Let's try to move on from there. Oh, by the way, just a quick thing. Notation. Notations are, when we have a function, we use parentheses. When we have a function, we use square brackets. Okay, that's important to know that. Now, the second part of Hornberg-Kohn theorem, which is the one that's actually useful, that's where beyond existence, okay, to address your question. If you can write this energy as a functional of the density, and this is really the brilliance of this. Suppose that you are a magician, and you can sample every single density there exists somehow. The density that will correspond to the ground state will be the one that minimizes the energy. That's what the second Hornberg-Kohn theorem does. So if you have a way to sample all the densities in the world and calculate the energy corresponding to them, the one that yields the lowest energy is the actual correct answer. Yeah.
It feels sort of similar to the Lagrange mechanics.
It is. Absolutely, it's the principle of least action is they are related. Yeah, it's basically the way to prove this. Again, do you want the proof of all this? I'll provide it tomorrow. You will see that it's actually very simple.
Somehow I feel this looks like the definition of ground state energy. Why is it? Because ground state energy by definition is the least possible.
Yeah, absolutely. But remember, what it means is that all you need to know is the density. That's what's important there. It's actually, the question here, just me repeat, I'm not sure everybody heard it, says, well, but you know, that's trivial. That's the definition of the ground state energy. It's the one that yields the lowest energy from all the densities. But no. The ground state energy is the one that you will get from solving the full Schrödinger equation with the wave function and everything. The point here is that you can also use a density as your variable, if you will, as your function, to find that ground state energy. And in fact, that ground state energy will be the lowest you get from the density. That means that if you were a magician, as I said, and be able to sample all the possible densities, then you will get the right answer. That's what it means. So it goes beyond just a definition, because that would be the right answer you would get from solving the Schrödinger equation. Make sense? Okay. All right. So, this is what it means mathematically. I always like to show this. This is kind of stuff you can put on your napkin when you have Thanksgiving dinner with your grandparents, and it's, look how smart I am. I can write this. I don't know what it means, but it looks good. So this is basically, this is a functional derivative right there. Okay? And I'm going to go behind the camera. That way I can see what I'm writing there to see it's correct. Yeah, look good. So you have here the energy functionals minus this term here, which is, this is just to see, I'm going to see here. What is this? There's no potential there. Oh, chemical potential. That's what you said? Chemical potential? So who threw the other one under the bus? This is, okay, this is actually a Lagrange multiplier. The Lagrange multiplier makes sure that you have the right number of electrons, because of course the integration of the density gives you the number of electrons. And it turns out in this case the Lagrange multiplier is the chemical potential of your system. And for people who have done statistical mechanics before, you know that there is a one-to-one correspondence between the number of particles and the chemical potential. You know, these are just reverse yin and yang of the same concept on how you calculate this. So basically, the problem here is this. This is the Hornberg-Kohn theorem number 2. It says that the minimal energy under the constraint of keeping the number of electrons constant, n, of course, otherwise you would have no electrons, therefore they do not interact, okay? That thing, okay, is the density that's correct is when this is equal to 0. Now, one thing that you can do here, and then we'll do it tomorrow, is that the functional derivative, so it's a really different beast than what you're used to, the functional derivative. The functional derivative of this integral is 1. This is the simplest result you can get for functional derivative, by the way. Okay? So the functional derivative of an integral of that function is 1. Anyway, there's a reason why this is equal to mu right there. Okay? So this is what you have to do. Okay, so everybody is okay with this? So basically what we've done is simply say the density is not only sound intuitively the right thing to calculate, but Hornberg-Kohn theorems establish that indeed this is exact. There is no approximation here. It's exact that if you are a magician and can calculate every single density is possible, you will get the right ground state and you will solve the problem exactly. So I like to insist on this. It would be an exact solution. So there will be a one-to-one correspondence with experiment, prediction or interpretation.
You don't have to go through switching calculations.
Well, we will have to go through Schrödinger equation to calculate E. We're going to get there in a few minutes. That's the catch. So far, it was a good news. Yes, there was a question. You had a question, no?
Yeah, so if you do it this way, I'm guessing there's some kind of approximation coming up. Because it
Yes.
seems like there's no way to go lower than the ground state. So the lowest answer is the closest one you can possibly.
Yes.
Right?
But there is a catch. So you are wondering if it's so perfect, why didn't I hear about this before, right? Well, it's pretty good. That's the reason why people use DFT so well. But the reason why it's good is because even though calculating the energy as a function of n is complicated, the approximation to do so are very accurate. And this is where I'm jumping now. You know, I talk a lot, so I usually like to take a 3-minute break after 50 minutes. So we are going to take a 3-minute break, and then I'll start and do the rest. Okay, let's keep going. So what's the catch? Well, the catch is that the Hornberg-Kohn theorems are wonderful, but they provide you no recipe or nothing how to do things. They just tell you if you can calculate that energy as a function of the density, you're in good shape. But we don't know how to do it. So it's like a mathematician love this because it's an existence theorem, right? It doesn't give you a recipe. And so everything came after this as a second part of these theorems, and Walter Kohn was still involved in this, and this is the second part that I'm going to talk to you about, is how to do it. And mathematically, this is what we have, okay? Just to remind you, this was my Hamiltonian to start with, and then we have those 3 terms, and now here's the big problem. The big problem is the density does not show in any of these equations. Okay? So you know a functional of the energy is an eigenstate of the Hamiltonian, right? But my Hamiltonian is not expressed as a function of density. So if I had a term that's psi square, I say fine, psi square is density. So it's easy enough to translate from wave function to density. Okay? But the problem is that these operators, especially, well, all of them actually, especially this one and this one, they are not expressed as a function of density. One is expressed as a Laplacian on single particle states. The other one here is just the distance between 2 electrons. I mean, there's no density showing up explicitly. So basically, you know that if you could express the energy and the Hamiltonian as a function of density, you could solve the problem completely, but you cannot. You don't have that. Mathematically, if you could just write all these 3 equations, which are the 3 terms here, as a function of density, then the problem would be easy. The problem, we can't do that. And this is where the next theorem will come into the game. That's going to be great, right? The problem is, of course, this. How do you calculate the interaction between two electrons when you know the density? Right? You don't know where the electrons are. It's just forming a density, right? Let's try to see in a second. Well, it works. So now there is a term that we know how it works as a function of density. To give you an idea, is the interaction between two electrons. The interaction between two electrons, if you know the density of electrons, you can actually calculate this. You recognize this, right? You recognize that this is simply the integral of n of r over dr is just the, is what? Is the electron, is the charge of the first electron, and the other one is the charge of the other electron. So as many electrons we have, which in this case 2. No, in this case, we have a certain density of electrons. So this one actually is a good approximation for the electron-electron interaction. In fact, our friend the chemist used this. This is called the Hartree potential, right? You recognize the Hartree potential is right there. This is the Hartree potential. Yeah, it is. This is the Hartree potential that's used by quantum chemists. This is probably a potential you've seen when you solve the helium atom in approximation theory, in a first order approximation theory in quantum mechanics when you were in preschool or maybe first year primary school. So this is great. So you can actually approximate that interaction between electrons with this. Well, the bad news is you actually, no, the good news first. Always the good news first. You do capture about 80 to 90% of the energy with this. Wonderful, right? The problem is what you do not capture is all the fun part. This is purely classical. This term there is a classical term, right? So everything that comes from the fact that you have quantum is completely gone from this equation. So we need to do better. But at least you know that one term of the Hamiltonian can be expressed as a density. So that gives us already an idea how the energy could be a function of the density. This is one term. Okay. Now, the problem also, and this is a very, very acute problem, is the Pauli exclusion principle. The Pauli exclusion principle tells you that the wave function of a fermionic system is to be antisymmetric upon exchange of the position of two particles. You know that, right? So the difference is that if I exchange I and j, my wave function changes sign. In terms of observable, you don't care because the psi is going to be sandwiched left and right to the operator, so the negative sign is going to disappear. But in terms of state, you actually do something. So how do you enforce this on the density? How do you enforce the fact that you have Pauli principle on the density? This is a very tough problem. In principle, exactly, it's essentially, I see people say, no, you can't actually do it very easily. So, and I'm going to draw, again, a comparison because some of you know about Hartree-Fock. In Hartree-Fock, this is an easy problem to solve because Hartree-Fock use orbitals, and they calculate anti-symmetric wave function by calculating determinant, because a determinant, Slater determinant, for those who have heard about this, a determinant is an anti-symmetric object. How do you know that? Well, if you exchange two columns of the determinant or two rows, you change the sign of the determinant, right? This is linear algebra. So this is why the Slater determinant works so well. And this is called, actually the initial approximation was the Hartree approximation did not have this anti-symmetric part. So the Hartree potential was the potential I showed you in the previous slide. When Fock came and said, well, you need to actually do the anti-symmetric thing, calculate the Slater determinant, then there was a correction and everything worked well. So this is why, this is the typical Hartree-Fock approximation that chemists use. So let's go back this. So Pauli said this, and this is actually easy to demonstrate why it should be like this. It's very hard to to actually enforce this when you know the density. So that's really something that we are going to have to struggle with when we try to express the Hamiltonian as a function of as a functional, or the energy as a function of the density. So, well, I already said that. Here, huge exchange. Yeah, you see, it did all this. Okay. Now, these are the difficulty with the electron-electron interaction. So just to summarize what I just said in the past 5 minutes. Electron-electron interaction, it's 1 over Ri minus Rj, sum over I, sum over j. Fine. We know that the big chunk of this is called the Hartree potential, is the double integral, the density at R, density of R prime, divided by R minus R prime. This is the big chunk of it, Hartree potential. We already know that stuff are missing from there. One particular one is the exchange. The fact that my density should reflect the fact that it should correspond to a wave function that's antisymmetric upon exchange of two particles. We can't do that easily. That's first part of the problem. Now, second part of the problem is the kinetic energy. The kinetic energy is this, and we have the Laplacian right here. So this derivative is a pure derivative, is a derivative that's purely acting on a function, on a wave function. So how do we make it so that this effect is on the density? Remember, the density is the integral of the wave functions. So how do you do that? Well, the bad news is that you don't know how to do that. Back in the days when I was a postdoc, so many years back, we tried to work on this and find approximation for the kinetic functional theory. It's not going anywhere. It's very difficult. So basically finding an expression of this that depends only on the density. We know it should be possible, but we don't know what it is. So by the way, and I'll say that again, there are some approximation. If any of you find a solution, that's probably a Nobel Prize, by the way, just so pay attention if you want a Nobel Prize, it's a possibility. Okay, now, this is the second part of the big contribution from Kohn. And that time Kohn was working with Sham. Sham is still a professor, is in California. And this is the second thing that he actually solved that problem of finding a way to calculate the energy as a function of the density. Okay? So what I did the past 10 minutes is try to convince you that it's indeed very difficult to calculate the energy as a function now of the density. Okay? Now here is the recipe from Kohn and Sham. And these are all the theorems. And these come from something very smart. Here is the idea. The idea is if my system was non-interacting, so if I had a collection of electrons that are not interacting with one another, it would be trivial to calculate, to get the density. And we know that because it's essentially solving the same problem n times. Okay? So Kohn and Sham said, okay, therefore let's rewrite my problem as if it were a non-interacting problem. Okay? Let's try to see that. We are going to say as if it was a non-interacting problem. So what Kohn-Sham did for the non-interacting system is say, okay, the energy functional is a kinetic energy functional of electrons that do not interact. That's something that's very simple to do because the density of each electron actually can be calculated very easily. It's just the square of a single particle wave function. There is this term here that's the interaction of an electron with the external potential by the ions. That one is a classical term, so we can definitely write it as a functional of the density. And then there is the Hartree energy, that are the one I introduced to you. That's also a classical term. Okay? And then you are missing stuff. You know you are missing stuff there. You are missing the fact that you have an anti-symmetric wave function, and you are missing some interaction between electrons. Maybe you're missing some other correlation. And you say, okay, you know what? That term is small anyways. I'm not going to put it to 0 because if I put it to 0, I basically don't do quantum mechanics anymore. But I'm going to say, I'm going to sweep everything under the rug of exchange correlation energy. So by doing this, I know how to calculate this, I know how to calculate this, I certainly know how to calculate this, and this would all correspond to non-interacting particles. And everything I'm missing, because I know I'm missing stuff because clearly the electrons are interacting, I'm going to put it right here, okay? In what's called the exchange correlation functional, okay? So, the idea behind this is that maybe we can build something here that be a good approximation for my problem. So why is it so good? Well, it's so good because now we have actually defined a new problem of non-interacting particles that exists in a potential that's fictitious, it does not exist, but if it's correct, it will reproduce the right density and therefore the right everything. Okay, and so this is what Cohen-Sham did. So the Cohen-Sham, that's how it happens, is that the exchange correlation functional, the piece that we don't know, is the exact solution minus what we know. I know, it's kind of it's not very useful to say that. But the known stuff is the kinetic energy of the non-interacting particles, the Hartree energy, plus the interaction with the external potential. That's the problem that we have to solve. Okay? So exchange correlation should account for all the quantum effects, and then also of a term that I didn't talk to you about, which is the self-interacting term. Oh, by the way, I should tell you about self-interacting term. In Hartree potential, we have a self-interacting term. Remember, what's the Hartree is the double integral of nr prime over absolute value between r and r prime, right? Suppose I have a single electron. I can have a single electron. That term should be equal to 0, right? The electron does not interact with itself. But it's not 0. Clearly, it's not 0, right? There is a density for a single electron, so density of electron times the density of the same electron divided by the distance of the integral is not 0. So it's called a self-interacting integral. That part, that term, self-interaction term, is compensated, should be compensated by the exchange correlation term. So just that should tell you that indeed there is a problem, the exchange correlation term is never 0. It should be at least taking into account this self-interaction term. Okay, now here's what Cohen and Sham did in addition to this, and it's called the local density approximation. So the idea is Cohen and Sham said, you know what, the exchange correlation functional, I don't know what it is, but let's use one that I know. And what they said, let's suppose I have a uniform electron gas, and you probably have seen in physics we like to simplify stuff a lot sometimes, right? By the way, that was the main reason why chemists don't like that, because we use something very, very approximated. So basically, let's suppose I have a uniform electron gas, and there is an analytical solution to that for the quantum mechanical problem. So what basically is saying is that the exchange correlation functional that I was telling you, so all the stuff I don't know, I'm going to borrow the one from a uniform electron gas. Okay? And I'm just going to plug it in. And if my system is almost a uniform electron gas, in other words, metals, for example, maybe I'm going to capture most of the physics. Okay? That's the idea. That's the idea. So that's called the local density approximation. So why local density? Because the energy only depends on the density of electrons at that given point where I'm looking at it. Of course it does, since it's uniform, right? It turns out that LDA, the local density approximation, works amazingly well. What do I mean by works amazingly well? What I found experimentally and what I get from this theory almost match perfectly. So that's quite amazing. That was the big surprise, is that even though the problem was impossible to solve, by rewriting it as a functional, by putting all the terms I don't know into one object, and by approximating that object by something simple, I could actually predict what nature does. That's amazing. That's why density functional theory is so popular, because actually it works, okay? So it turns out people wonder, why does it work? It should not work so well. You are using such a crude approximation. And this is why chemists didn't like it, by the way. That's why they didn't like it. Don't talk about, you can talk about DFT to chemists now, but certainly don't talk about LDA. They will look at you and they just probably send you some chloric acid or whatever, some stuff they use in you know, stuff like that. And you can throw electron at them, it's not going to make a difference. So it makes no sense. Why should it work so well? And then, of course, you have great mind who said, of course it should work well, because, by the way, it's much easier to make a prediction after the fact. Have you ever noticed that? Yeah, I know, right? It's much harder to make prediction about future stuff, somehow. People said, well, but you know, it's very simple. It's because the exchange correlation functional that you're using is an actual solution of a true problem, which is true. It's a uniform electron gas. So basically what happens is that when you do this, you are essentially, you're making a lot of mistakes. But because it's a correct answer to a given problem, all your mistakes are compensated by other mistakes. LDA is probably one of the best examples where cancellation of errors works the best in your favor. I am not kidding, this is really true. So what happens is that the numerical values you get are extremely good for the wrong reasons, but they are good because everything you're using, all the ingredients you're using in your theory meet what we call the zero-sum rules, because they are also solutions of your differential equations. Therefore, you are certain that the integral over the entire space, if you will give you the right answer at the end. Okay? So, it's not as gloomy as it sounds, by the way. It's just the luck is that because LDA was so accurate to start with, that prompted other people to make it even more accurate for the good reasons. So that's what came up after that. You know, you have to look at it from a historical standpoint. So drawbacks of LDA. It turns out LDAs tend to overbind. So if you calculate the structure with LDA, you are going to find that the bond lengths are going to be shorter than they should be. When we say shorter, we are talking about a few percent. We're not talking about 5 angstrom, okay? So for example, for carbon, instead of having in graphene, for example, instead of having 1.42, you might have 1.39. That's what we're talking about, right? It's maybe a couple of percent. But it tends to overbind. So in terms of the elastic properties and so on, it tends to make structures stiffer than they actually are. But that's what LDA does. Another thing is that the electrons are not localized enough in space, and that's a big problem. So LDA, because it's an exact solution for a uniform electron gas, tends to spread electrons more than they should be. Okay? That's a big problem. That's a big problem because if you have systems that have strongly correlated electrons, they correspond usually to high density of electrons at given spaces. So in other words, sharp distributions. So everything that's very strongly correlated, like for example superconductor or some other system like that, are completely ignored by LDA. LDA will not be able to do this simply because the electrons are basically too spread. Okay? Of course, everything that has long range is completely missing. So again, same reason, local density, I mean, the name kind of give it away, right? Local density approximation means that you only include what's happening locally. So you have no non-local effect. So what happens here only depends on what's going on here. So for example, van der Waals interaction, so those dipole-dipole interaction, for example, or instantaneous dipole interaction, completely gone from LDA. There is no such thing as van der Waals interaction in LDA. Okay? I should also tell you that there are so many people who says that LDA is great for van der Waals interaction. but it's not. Why do people say that? Well, here is the deal. LDA overbinds. So, in other words, tends to delocalize electrons too much, and therefore you have more overlap of electrons than you should have. So take two pieces of material that interact by van der Waals interaction. Van der Waals correspond, as you know, 1 over R6, you know this is the deal. Because the electrons are too delocalized, there is some overlap between the charge density of this object and this object. Therefore, you have an attractive term between them because of all the constellation, as I explained before. So you do actually include an interaction between them that turn out to be almost the same as if you had van der Waals correctly. Okay? So it turns out that the structure you get is almost as if van der Waals was perfect. But in fact, there is no van der Waals. This is a perfect example of big constellation of errors. The interaction, the structure looks right, but the interaction that's responsible for it is completely incorrect. Okay, so this is a problem with LDA. The next approximation that I hope to have time to talk about in a couple of minutes is called a general gradient approximation, where we add not just the density, but the gradient of the density. That one also misses van der Waals, but it also delocalizes electron less, is better at that. So when you try to do van der Waals interaction with GGA, you don't have van der Waals interaction. In fact, if you put those two objects, you know they should interact by van der Waals. In LDA, they're going to give you the right answer for wrong reason. In GGA, they're going to go away. So conclusion, LDA is much better than GGA, right? I mean, this is the obvious conclusion that everybody reaches, but it's wrong. It turns out GGA is much more accurate, therefore you don't have the right answer. That sounds wrong, right? But this is the way it works. So this is where you guys, all of you are grad students, right? Most of you are grad students, or at least you are interested enough in the fields of computational physics and so on to be here for 3 weeks. I mean, come on, that's some dedication. So, all this is your responsibility to make sure people do not propagate misconception, not necessarily in DFT, because some of you will never do DFT in their life, fine, but in your field, you are responsible. You are actually carrying the torch of truth. Oh, that's too much. You are actually responsible for being a beacon of hope. It's even worse. Okay, but you get my drift. No, I'm not kidding. It's important that you actually use your knowledge to make sure that misconception remains out of the landscape. Okay. Yeah, the hydrogen one is also wrong. So happy physicist versus grumpy chemist.
No.
So for many decades, LDA has been applied in calculation of band structure and total energy in solid-state physics. In quantum chemistry, it's less popular because it's not accurate enough. It turns out that DFT and LDA kind of capture most of the physics right, but the numbers do not meet the many digits that chemists like to see. So instead, they were using what's called not so much Hartree-Fock, because Hartree-Fock, of course, is also kind of antiquated method. Molar placet on top of Hartree-Fock, or even couple cluster, or even beyond that. So, which is really what they consider ab initio. So if you talk to a chemist, ab initio is not DFT. Ab initio is MP, whatever, molar placet, or a full CI, or things like that. Physicists, DFT is first principle in ab initio, just so you know. So don't be surprised if you ever in the field. Okay. So, just one more thing that I would like to talk to you about. In solid-state physics, we are interested in the band gap. So basically, why are we interested in that? Because of the semiconductors. Solar cells, the band gap is important, is how much energy you can actually get from the sun, for instance, or if you want to make a device. If you want to make a transistor, you need to know the band gap. For example, silicon. Anybody knows the band gap of silicon? You should know that, right? 0.
0.5 gap.
This is part of the culture, right? What's the band gap of silicon? 0. How much?
7.
You have a good advisor. Yes, correct. 50% off.
I still might order
I mean, you should know this stuff, right? There are some not necessarily bad silicon band gap. It's like how much energy do you have at room temperature? What corresponds to room temperature? What's kT in, let's say, in EV? Who knows this answer?
25 electrons.
Thank you. Somebody knows the answer. You should know that answer too. These guys too. You forgot already? Okay, good. Thank you. It's great. It's great. So 25 millieV is indeed kT. That's another thing you should know. And that one is important because if you do statistical physics. I mean, these are things you should just come, right? Okay, band gap problem. Okay, band gap is important because we want to make devices, and you spoke, you know, Eduardo Cruz was here last week, and he's in his company, the company he works for, you know, they want to have calculations so that they don't have to create the wafers because it costs millions of dollars to make them. They would rather hire somebody to do the calculation and tell them, no, don't do this, don't touch it, because you save money, okay, and time. Here's the problem with LDA. This is the experimental band gap horizontally and the LDA band gap vertically. So if there was a one-to-one correspondence, they will all be on the bisector, right? Well, not quite. Unfortunately, you see that LDA badly underestimate the band gap of most material. So the amount of energy you need to excite an electron, this is the band gap. Well, that's pretty bad, actually. It's always underestimated. The underestimation is about 50%. So probably from DFT 0.5, actually, you're probably close. So let's see, silicon. Yeah, actually, you had the LDA band gap. So that's correct. Right? There are even some that actually tells you the band gap is negative. How can you have a negative band gap? Yeah, it's pretty bad. I saw some. Ooh, yes, indeed, it's pretty bad. So that means basically that you predict semiconductor to be metals. That's what it means. So that's pretty bad. So LDA is not great for that. Now the problem, remember, the problem is that we don't know what this guy is. So here, we know there is an error in the energy because we don't know this one exactly, and energy and potential. So people came up with different things. So I like this slide because it's very clear and very simple. This is a picture that John Purdue from Temple University came up with. So John Purdue said, he's a physicist who develops those exchange correlation functionals, okay? Very world-renowned person doing this. LDA is a simple approximation. So he has this Jacob's ladder, as he call it. So the Hartree world is right here, where there is essentially nothing. So Hartree is basically the energy without the exchange correlation, right? So if you put LDA, if you use LDA, you have here. You can then use GGA, it's called general gradient approximation. You also include the modulus of the gradient of the density. Then you can go above. We're actually about here right now, but computationally speaking. So basically, you can improve this exchange correlation. And to be honest, it's a full-time job to go there because it becomes more and more complicated. But the point is that you can refine this. And why did people refine it is because LDA, in spite of its amazing simplicity, already captured most everything. There were problems, there were constellation of errors, they are still there, yet they seem to capture most of the physics. So any improvement could actually improve the physics, and this is where we are right now. So we have a number of meta-GGA that works, like for example, scan is a meta-GGA functional. There is also others that's called hybrid functional that I can talk to you about later, tomorrow. So the point is, you can get all these functional, and of course I'm not going to get into details here. The point is that it becomes a numerical problem, really. You have to calculate all those terms. But the reality is that you get a package, a DFT package now, that allows you to get very accurate prediction of all those numbers. So, and you get the physics right. That's what the beauty. That's the beauty behind it. So if you ever use a density functional theory package, you really need to know what exchange correlation functional you are going to use. It's the same as if you were getting a car and you don't know what kind of gasoline you have to put in there. So if you do not find a tank, that means it's probably an electrical car. You should probably know that when you buy it. If you need to put diesel in it, don't try to put gasoline in it. It's a bad idea. The opposite is even worse. If it's a diesel and you put gas, right? You've tried that too, right? Yeah, it's not good. So you basically have to buy a new engine. So that's, and the problem with the calculations though is that if you do that in a calculation, it lets you do it. It lets you do it, no problem. You're going to get a beautiful graph, completely. What should I say? Oh, you are creating new physics. Yeah, I always tell students, if your calculation demonstrate new physics, before getting too excited, check that you've not done anything wrong. Yeah, don't let other people tell you it's wrong. Try to tell yourself. Okay, so this was basically my last slide for today. Tomorrow I'll continue with what I have, and I would like to spend I will actually prove the Hohenberg-Kohn theorem to you and spend a few minutes on functional derivative. This is a big thing. Try to put it in 3 hours is a challenge, especially that I like to keep your interest. And as I said, you have a lot of information over those weeks. So I just hope that you have an idea a little bit that people can get excited about DFT. So I'll talk to you tomorrow. Thank you. I told you, now you regret it.